Hi folks, welcome back to Physics with Captain Rod. I'm making this video here as part one of a two-part series here on principles of work and energy. And let's see, what we're going to do here, we're going to take a look at this child, this example where this child accelerates down this hill on the sled. And given the fact that this hill is basically 10 meters high and the child starts from rest, we're going to apply the work energy theorem and use it to predict the speed of the child at the bottom of the hill. So the work energy theorem is a theorem about different states, and here's what we mean by different states. Like this position here, which I'm going to call position 1. The child is at a certain set of coordinates as measured by some coordinate system, and they have a velocity of 0 at that point. So that's kind of what I mean by a state. State 2 here, the child's at the bottom of the hill, its coordinates are changing, and now the child's got some velocity vector here. So I'm going to go ahead and write out the work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2. And I'm just going to go through this kind of term by term. So PE1, right, anytime you're dealing with potential energies, you need to define a datum. So I'm going to go ahead and do that. And I'm going to go ahead and define the lowest point in the diagram basically here, my datum. Do this in green. So there's my datum. That means that PE1 is going to have a positive potential energy because we're above the datum, and that potential energy is going to be a gravitational potential energy equal to mgh. KE1 is 0 because in this example the child starts from rest. Leave a little space if you're taking notes on this. I'm going to come back and talk about that work term. Equals PE2. So position 2, we're down here, we're at our datum, so I'm going to go ahead and put 0 for PE2. And then KE2 is going to be 1/2 mv squared. Now I could call it 1/2 mv final squared like I noticed I did in this picture, or I could call it 1/2 mv2 squared because it's at position 2. Now there's really only one velocity that's going to show up in this equation, so I'm just going to leave it v, but that v here needs to be understood is in position 2. Now the work term, what do we do about that? So the work term is generally reserved for external non-conservative forces. There are potentially forces acting on this sled as it moves down the hill. One, air drag. What do we think about that? So that's one that I'm going to just assume away. Air drag forces are forces that are speed dependent. This probably will stay in a relatively low speed situation, so air drag is probably not that important. Another possible force is maybe a frictional force between the sled and the surface here. So I'm going to assume it's really icy and that the frictional force is approximately 0. And those are the only two forces I can think of that could conceivably change this energy equation here. Another significant force acting on the sled is the normal force. However, the normal force doesn't do any work because as the sled goes down the hill, the normal is always at a right angle to the velocity. So these are the only two forces that have potential for doing work. I'm going to assume they're both small in this example and therefore put 0 for the work term. All right, so here's our work energy equation applied to this problem. The next step would be to just go through it and simplify it. We don't need the zeros, and also the mass is common to both terms here. So it simplifies pretty fast. Boils down to basically GH equals V squared over 2. And it's pretty easy to solve for V. Actually, I'll just solve it for V squared. 2GH. And since I don't like radicals, I usually just put in my numbers at this point. So that's going to be twice 9.8 meter per second times a height of 10 meters. I'm going to go ahead and calculate a value. And I get about 14 meters per second out of this for speed. Now, unit-wise, very important to pay attention to units. So the 2 doesn't have any units. The 9.8 has units of meter per second squared. I'm just going to take a look at this off to the side. And we're multiplying that by meters. So we end up with meters squared over seconds squared for the units on this calculation. because it's v squared equals, that's exactly what we're looking for. And then by the time you square root that, you get meter per second. So what this stuff means in a, I shouldn't say perfect world, but in a world where air drag is negligible or close to zero in an extremely icy surface, so that frictional forces along here would be approximately zero, the child should reach the bottom at about 14 meter per second. I hope this video helps demonstrate this concept. I'm going to make a part 2 to this where we talk about this stuff here. So hope this helps. Have a great day.